my name is Damien Thompson. I'm a lecturer in the physics department in UL. And just like you, just like all of us, I hate disease. I hate illness, I hate sickness. And I particularly hate illnesses that affect older people, because these are diseases that are not actually subject to evolutionary pressure. From the point of view of natural selection, you don't matter anymore. You're beyond the point at which you usually reproduce, so your genes don't care whether you live or die. For many of us, we're destined to die a very slow and undignified death, where plaques build up in our brains and we start to lose our personalities, we lose the ability to live independently. And I hate that. I think that's a horrible way to go. Thankfully, medicine is actually becoming molecular now. So we are starting to learn how these diseases progress. And it's my hope and my belief that within 5 to 10 years, neurodegenerative diseases, these diseases that arise from neurotoxic proteins forming plaques in our brains, will actually become something like AIDS. So it will no longer be a death sentence, it will be something that people live with. It will be something that's managed through drugs. I'm here today with two of my group, Cheyenne and Jose, who are going to tell us a little bit more about the techniques that they use to build models for these neurotoxic proteins. And it's our hope that we can use these models, once they're good enough, to actually design new drugs that have a hope of actually stopping diseases like Alzheimer's and Parkinson's in their tracks.
In 1906, Dr. Alois Alzheimer first described the symptoms of the disease that would carry his name. After studying for 5 years the decay on the brain of one of his patients, named Auguste Deter, the autopsy of her brain revealed a high amount of plaques that were demolishing the structure of her brain. This would set up the pace of the research in neurodegenerative diseases for the next 100 years.
Since then, the scientific community has been taking special interest in a new class of brain disorders, now popularly known as the neurodegenerative disorders. It's been over a century now, and though we have come up with some plausible explanation of how this disorders progresses, we are yet to synthesize a novel drug that would effectively treat these disorders or prevent them in any case. A baffling question in this regard being, how do the proteins in the brain manage to stick to one another and give rise to plaques? But first of all, we need to look at what exactly are these sticky proteins.
Proteins in general are the basic building blocks of the organism. They take care of the structure and function of the different organs and tissues in all of the body. They usually are composed, much like a model is composed out of Lego bricks, they are composed of a long chain of amino acids. These chains can be hundreds or even thousands amino acids long. Then they will fold, adopting specific shapes that will help them carry on with their functions in the body.
Unfortunately, the proteins we are after do not. They tend to kind of wiggle and jiggle around, shaping themselves randomly and at most times losing their shapes. For this reason, they have got a special name, intrinsically disordered proteins. Almost 1/3 of human proteins are intrinsically disordered.
The main issue with these intrinsically disordered proteins, though, is that sometimes they will misbehave, misfold them, and shape themselves into very awkward positions that will cause them to actually stack up and form these harmful plaques in the body. They will wreak havoc among all of the body.
Especially the brain tissues, where these proteins kind of tend to clump on each other, giving rise to large aggregates and then plaques over time. This disrupts the usual balance between making and breaking of proteins, but that's not all. This leads to lethal and debilitating neurodegenerative disorders like Alzheimer's, Parkinson's, Huntington's disease, Prions disease, you name them.
The problem is we know very little about these sticky proteins, what makes them tick, what makes them stick. We are working with research laboratories all across Europe to try and figure out exactly how to study these proteins and how to figure out what makes them work and how to stop them from sticking together. The problem is most traditional research methods are not very good at actually figuring out what these proteins do. They are very hard to catch through experimental methods, and even most of the computational methods that we've usually worked with have issues trying to figure out what they do. This is why we are working to research and develop a new method of working with these sticky proteins.
In order to carry out this task, you would want to have the proper theoretical tools. And fortunately for us, computer simulations, or more precisely molecular dynamic simulations, provide the means to record the time-dependent behavior of these proteins as it would have taken place inside the body. We are using resources from the Irish supercomputing facility iCheck. There are a number of options available when it comes to simulating these proteins floating in water, and part of our work is to figure out which one of these works best. For instance, a major decision to be taken in this regard is to create the right kind of protein-water interactions. This is to make sure that the proteins do not behave abnormally at any stage during the simulation, such as collapsing into a ball or completely unraveling themselves. We count on our methods to do just that, and we have been working hard to get there.
When we figure out the way to properly model these proteins, how to properly get them to work and how to get them to behave in the computer as they would behave in real life, the next step is to figure out which of the shapes they take is actually these misshapen forms that will make them stick together. For this, we will take the steps to research their surface, see what particularly interesting properties they have, and specifically what makes some of these shapes stick to each other. Once we know what will make one of these shapes stick to each other, we can figure out from these forms, from these surfaces they have, how to design drugs that are specifically targeted to this kind of shape and keeps them from sticking together, keeping these plaques from forming in the first place and preventing all the cascade that results in damage to the brain.
So as you can see, this research gives us ample opportunities to put to good use the state-of-the-art methodologies in computational modeling, ranging from informatics to simulation to drug design. Not only that, our experimental partners in Madrid, Spain, can put to good use our finding by synthesizing novel drugs and testing their efficacy against these proteins sticking to each other and aggregating to form plaques. This is promising to provide real societal benefits in fighting with one of the major illnesses of the 21st century and offer hope to age gracefully. I have been Shayan.
I've been Jose.
So that must make me Damien. So there you have it, from the horse's mouth. Growing old gracefully, using computers but without becoming cyborgs. Sounds good to me. If you'd like to know more about the type of work that we're doing here at UL, please do not hesitate to contact us. We are eminently Googleable. Thank you very much.